Today we're talking about approximating square roots. So in the beginning of this chapter we talked about square roots and how to find square roots. And remember that square roots are when we have a number times itself to get to the number we're looking for. So a rational number, let's first talk about irrational numbers and irrational numbers. A rational number is a number that can be written as the ratio of two integers. So for example, 1 over 2. 1 over 2 is a half. That would be a rational number. An irrational number cannot be written as the ratio of two integers. So one of the more famous numbers that we talk about when we talk irrational is pi. Pi is an irrational number. There's no way to write it as a ratio of two integers. So while we're going to look at the following numbers and decide whether they are rational or irrational. So square root of 16. Well, the square root of 16 is 4. 4 would be a rational number. One way that you might want to remember this is that if I look at a number, like the number 4, and I think that it is 4.0, the next number following that would be another 0, and another 0, another 0, another 0. We can say that this number is rational. It's acting rationally. When we think of somebody acting rationally, they make sense. We know what's coming next. They're kind of predictable. So the number 4, which could be written as the ratio of two integers, 4 over 1, we can also say is a rational number because we know what it's going to do. Let me jump forward to 2/3. So 2/3 as a decimal is 0.6666 forever. So we know that 2/3 is 0.6 with the repeating bar. Now, sometimes we get confused on whether this is rational or not, but really, it's acting rationally. We know what is coming next. We know that after each 6 comes another 6. So even though it's repeating and continuing on forever, we know the next digit is 6. So it is also acting rationally. On to the next one. When I look at 0.25, well, this decimal is a terminating decimal. If I was to continue it, though, we know the next number. It's a 0, followed by another 0. As soon as it terminates, there'll be zeros from there on out. Again, this is something that is acting rationally. Another way to write this number would be 25 over 100. Again, two integers. The next one we see is 0.94 with that repeating bar. So this means that this is going to continue on acting very rationally. After the 9.4 comes another 9.4, followed by another 9.4, etc., etc., etc. So again, very rational. We know what's coming next. The next one, cube root of 8. Well, we did the cube root of 8 in the previous section. We know the cube root of 8 is 2 times 2 times 2. 2 is definitely a rational number. I can write it as 2 over 1. So another rational number here. Jump over to the next one. The next number is 6. It's a terminating decimal, 6.0. Can easily write it as an integer ratio with 6 over 1. Again, rational. Now let me just bounce back to the two we haven't touched on. So we have the square root of 7. Well, the square root of 7 is not a perfect square. It's actually going to be a number that when we multiply, and we divide it out and we get what it looks like, it's actually going to go on forever, but it's not going to have something that we can predict the next number. Any number really that is not a perfect square, and in this case it would have to be the 4 or the 9, we're going to say is an irrational number. The same thing with the cube root of 30. If I had the cube root of 27, it would be 3. But this number, again, is going to be an irrational number. It's going to be a number that kind of goes on forever, but there's no pattern to it. There's nothing that we can predict. So just like with pi that we started out with, pi is irrational because if I look at that decimal, it keeps going and going and going, but we don't have any type of a predictor of what the next number is because there's no repeating patterns. So down here at the bottom, just keep in mind, when you look at these, the decimal form of a rational number either terminates, meaning it stops, but then we know that it's zeros forever, or repeats. And remember, the word repeats means it goes on forever, but in a pattern of some sort. Rational numbers and irrational numbers kind of work together to form the real number set. Okay, so real numbers are broken down into rationals or irrationals. Rationals then break down into other types as integers, whole numbers, natural numbers, counting numbers. And the irrationals would just be irrational. We're going to learn about other number sets in future math classes, but not this year. So next, we want to look at classifying real numbers. We want to look at whether these real numbers are rational or irrational, an integer or a whole number. So really, your first thing is going to be to decide rational or irrational. So when I look at the square root of 12, it's not a perfect square, so this is going to be irrational. Now, once we say that it's irrational, it can't be an integer, and it can't be a whole number. So we're done. The next one, we're going to look at that negative 0.25 repeating. Well, as we just determined, this is definitely a rational number because it does have a repeating pattern. The next numbers make sense or are acting rationally. But the question is, are they an integer or a whole number? Well, we know an integer are all our positive and negative whole numbers. And the whole numbers are all the positive whole numbers, meaning no decimals or fractions. This is definitely an in-between of those, so this would not be an integer or a whole number. The next number, if I take the negative square root of 9, is negative 3. Well, negative 3 is definitely rational. It's also an integer, because it's the negative 3, but it's not a whole number, because remember the whole numbers would be our positives. So it is both a integer, and just keep in mind this is an integer, whereas this is irrational. I know I shouldn't be using the same I because that could be confusing. So an irrational versus an integer. Once I say something is irrational, there's no other integer or whole numbers to it. If I say it's rational, they can't be both rational and irrational. Then you move on to, well, is it integer or a whole number? So the next one. Well, 72 over 4 can be reduced, and it's definitely a rational number because we can write it as a ratio of integers. 72 over 4 becomes 18. So 18 is rational. It is an integer. It's also a whole number. So it's actually three of those, rationals, integer, and a whole number. And then the last one, pi, the most famous of all the pi's. Maybe I can just put an IRR, definitely irrational. And again, once I say that it's irrational, then there is nothing else that I have to do. So now we're going to talk about approximating square roots to the nearest tenths. We're going to follow the steps above to find the nearest integer. Then we're going to find the difference between our number and the lower perfect square. This difference is going to be our numerator. Then we're going to find that same difference this time though between the lower and upper perfect squares. This will be our denominator. We're going to divide the numerator by the denominator to get the decimal and round to the nearest tenths. We then put the whole number we first found and the decimal values together to get our answer. So what does this look like? Well, again, if I break this down and do the square root of 71, my two perfect squares just below it and just above it are 64 and 81. Well, we are clearly closer to the 64. So right away, I know that 8 is the nearest whole number, or integer. So here I'm going to look at the difference between the lower and my number. I get 7. Then I'm going to look at the difference between the lower and the upper, which is 17. So my answer is going to be 8 and 7/17. So what we want to do next is turn that into a decimal. If I divide 7 by 17, we get 8.41. The 1 won't make it high enough, so we would just round it to 8.4. So we would approximate this to about 8.4. So on this next one, we're going to go back to a negative square root. So we got to think again what that negative is going to do for us. So when I think number line, I've got to think the lower one, which is really the higher one if you want to look at it that way, on the number line is the square root of 9. The lower one would be the negative square root of 16. So now thinking about this on the number line, we've got to be careful here. The nearest integer, when you look at this as the nearest integer, it's actually going to be the negative square root of 16, because it's a little bit closer. It's only 3 away here. It's 4 away from this one. However, if I'm picturing a number line, so if this was actually on a number line, and we were to write this as a decimal, because we're on the negative side, we are actually going to be writing as if this is our lower of the numbers. So what I mean by that is when we get to our final answer, it's going to be negative 3 point something. Because we're on the negative side, it is sitting someplace between the negative 3 and the negative 4. So in this case, when I am now going to find my lower to our number distance, we are actually going to use that distance. And then the overall distance is still from the 9 to the 16, which is a 7. So again, this would be negative 3 to the 4/7. And negative 3 to the 4/7 is 3.57, which again, rounded, is negative 3.6. So we are approximately negative 3.6. If you go with the negative 4 point something, because you think of it as the closer one, it wouldn't make any sense, because negative 4.6, for example, would be on the number line someplace over here. Because as the number line goes on the negative side, negative 3, negative 4, negative 5, so negative 4 something is here, when our number is actually in between the negative 3 and the negative 4. So our answer has to be negative 3 point something. A little bit tricky. We'll take a little bit of practice. So on this next one, we want to know which is greater. Well, we can kind of compare them a little bit if you want by making them similar. 2 and 2/3. Well, hopefully we know that 2/3 of the decimal is 2.6 repeating. So let's just look. Maybe we don't have a calculator. What is closer? So what if I do the square root of 5? My two perfect squares that surround it would be the square root of 4 and the square root of 9. So this number is someplace in between the 2 and the 3. So we're not really sure yet what the difference is. If I look at my lower number to the R number, I have a difference of a 1. If I look at the 4 all the way to the 9, I have a 5. So really, we're looking at our number, meaning the square root of 5, is about 2 1/5, which is 2.2. So which number is greater? Well, clearly, 2 2/3 is greater than the square root of 5. Looking at the next number again, we can look at our first number by thinking of it as 4.2, and then let's focus on what is the square root of 23. Well, if I surround my numbers, square root of 25, square root of 16, which means it's someplace between 4 and 5. Now this time I'm a lot closer to the 25. This is actually 7, and overall difference is 9. And if I do 4 and 7/9, when I do my ninths, 7/9 is the same thing as 7 repeating, which is definitely larger than, so 4.7 repeating is greater than 4 1/5. So here's our last example. So we have a periscope. Periscope is what submarines look out over the water. So here we have the distance in nautical miles. You can see with a periscope is this expression right here, 1.17 times the square root of h, where h is the height above the water. Question is, can you see twice as far with a periscope that is 6 feet tall out of the water versus one that is 3 feet? Well, when you first think of it, 6 and 3 is twice, so maybe the answer should be yes. But let's think about that for a minute. If I do 1.17 times the square root of 3 and 1.17 times the square root of 6, what we're trying to find out is, are those two things basically double? So just on a calculator, 1.17, the square root of 3 is about 1.73, where the square root of 6 is 2.45. So while 6 and 3 are twice, 3 is twice the 6, 6 is twice 3. When we do the square root of 3 and the square root of 6, you can kind of clearly see here that they are not twice. 1.73 times 2 is going to be much bigger than 2.45. So because we are multiplying the 1.17 on both, we don't even really need to multiply this out. The answer is no, not twice as far. So yes, 6 is twice 3, but the square root of 6 is not twice the square root of 3.